Hi friends, today I'm going to prove an equation for centripetal acceleration which is already known. I'm pretty sure that you guys already know the equation, a relevant equation for centripetal acceleration, but using a special method, that is a vector method. So I'm going to use a vector method to prove this equation, actually the v squared, the centripetal acceleration is equal to v squared over r. So there are a few other equations as well, right? The next one is r or v omega or r squared omega. So any of these equation is applicable, but I'm going to prove this equation. So hence we can prove any other equation. So that's why I'm going to use the vector method to prove this equation today. Right. If you don't know anything about centripetal acceleration, I have a responsibility. So I'm responsible to explain more about centripetal acceleration. What is centripetal acceleration? We already know, guys. Let's imagine, right, if you already know physics a little bit, right, when any object moves in a circular path, I'm going to take a small circular trajectory like this, and I'm going to take a small object like this which is moving in this little circle and in this little circular path, right? What can we say about this one? Imagine when the angular velocity of this object is constant. So this one's here the magnitude of the velocity, or you can easily explain it as the speed of the object, which remains constant throughout the entire motion. So when this is v, and v, right? So then, if you want to, so now what can we say about the velocity of this one here? We already know, guys, the velocity is a vector quantity. Velocity is a vector. As velocity is a vector, it has a direction and a magnitude, which means both the direction and the magnitude must be considered, right? Then, even though the magnitude of the velocity remains unchanged here, we can properly see that the direction changes at every instant. At every instant, the direction of the velocity changes here. So what does it mean? The change in the velocity means, in order to change, velocity has two particular identities, or velocity has two things, as I said earlier, the direction and the magnitude. So change one component, either the velocity or the magnitude of velocity or the direction, means there must be an acceleration. An acceleration is required to change the direction of the motion, or the velocity, or the motion state, simply the velocity here. So then in order to change the velocity, there must be an acceleration. So what is the direction of this acceleration? You can see in every instant the direction is changing, which means so later on we can prove that the direction of this one is towards, or it is acting towards the center along the radius of this. So we can take it as AR. So this is the centripetal acceleration, which means in order to successfully complete this circular motion, a centripetal acceleration is required towards the center. Right. Now, let's use the vector method to derive this equation, which is already known for the centripetal acceleration. Right. Now, let us take right. So here now the previous moment of the object which is moving in a circular path, and what I'm going to take is I'm going to take that the angular displacement after some time is a theta or delta. It's a very I'm going to take a very small or a small instant I'm going to consider. So the delta is a very tiny angle, a small angle here. This is v and this is v, right? So now what can we say about the acceleration? We already know the acceleration can be described as the rate of change of velocity. So a is equal to the delta v over delta t. So somehow now I want to describe delta v separately and delta t separately here, right, in order to find the acceleration. Okay, now delta v is equal to here, you guys can already see that the direction. Now if you take this one as a horizontal one, a horizontal velocity component, what is the angle between these two velocity components? So this is delta and this is 180 minus delta, so therefore this angle must be again delta, that is delta. So then you can say that here the delta v here, the change of velocity, is velocity final minus velocity initial. So then I can write it as your velocity final, that is the direction of velocity final, and this should be dotted lines, and here my angle, and this is my v minus the initial velocity. Initially it was moving towards that direction, so it's very clear here. Okay, now the next important theory here that we need to realize is when you have a negative vector, instead of writing negative, you can make it positive by switching or opposing the direction of this v. So now how can I write this equation here is, how can I write this here? It's here delta and here v, and I'm going to switch the direction and I'm going to make it plus by switching or opposing the direction of this. Right now, a very familiar vector theory I can use here, a very familiar vector theory. When you combine them together, for the delta v, I can take a resultant value for this, a proper resultant. Delta v is equal to, here is this one, and this is my v, and this is my other v, and these two should be equal in magnitude, right? And this is my resultant, starting point and ending point. If you have no idea about it, you can watch one of my previous videos, or later on I'm going to upload another video related to vectors. I'm going to explain how these vectors work, or how can we deal with vectors, right? So those things, so no worries, you can learn later on if you want. So this is my delta v now. Okay, interesting. That is my delta v. Right. Okay. And last but not least, the next thing here is I'm going to consider this when this delta is a very small value. I'm going to ask a question. Now imagine the surface that you see in front of you. Just consider the flow that you see, the flow, right? The flow that you are standing right now, right? Which sort of surface is it? Is it a curved surface or a very horizontal surface? So I'm pretty sure your answer would be that is a very horizontal, or the horizontal surface. It's not a curved surface. Even though it is a horizontal surface, what can you say about the Earth surface? The Earth is something circular, something spherical. So then the surface should be a curved surface, but can we see the curvature here? We can't see the curvature. Why is that? As the angle compared to the entire Earth's surface, the angle the subtended by the surface that you consider is a very tiny one. A very tiny one. As it's a very tiny one, you cannot see simply the curvature of this curve. So then, almost, right, you can approximately take this surface as a linear surface, which is not exactly true, but that is an approximation when this delta is a very, very tiny one, a very small value. Right. Now the next thing is here, you can see now this is my radius, and this is my radius, and this is my delta, and here the distance this one travels here. So you can use our motion equations easily here to find that length, even though it's a the curved surface, a curved length or a circular length. We are not supposed to take it as a curved length here. So what is that here? The displacement here, the delta S. If you take this as delta S, the delta S is equal to V times delta T, right? Interesting, isn't it? V times delta T, right? Now I already know the angle between these two is also delta, and now I have two very similar triangles. So right, so I'm going to extend my working to here. So then I have two specific triangles now. So this is my V, and this is my V, and this is my delta V, and this is my angle delta. Right, my first particular triangle, I'm going to label it as here as you wish, anything, ABC, right? So then I have another triangle, this triangle. So I'm going to label it as, right, this is my other triangle, here R, and here R, sorry. And this is my V delta T, right? So this angle is also delta, right? Now you can clearly see that these two triangles are equiangular triangles. What are equiangular triangles? The equiangular triangles, when the interior angles, all the corresponding interior angles in each triangle are same. So you can say that those are equiangular triangles. So here these two triangles are equiangular triangles, so hence I can use the ratios. So if you are a math student, you might know, if you are a mathematics student, you might know that the ratio of these sides can be taken to work this out. So I'm going to use, so you can see now these corresponding sides or corresponding angles. When this is ABC, I'm going to take it as PQR, capital R. So now I can see that now here BC to PR, these are two corresponding sides, BC to PR, and AB to QR. So AB to QR, these two are two corresponding sides. So then I can say that now the BC, right? I should use the black color. BC over QR, BC over QR is equal to AB over QR. Oh, I made a mistake, sorry. BC over PR, sorry, that's a slight mistake. BC over PR is equal to BC over PR is equal to AB over QR. AB over QR. Right. BC. The value of the BC here is delta V. Delta V over PR is V delta T. V delta T is equal to, on the other side, AB is V over R. Right. Now bring this additional V onto other side. So delta V over delta t is equal to, when you bring this on the other side, it becomes v times v squared over r, right? This is what I'm expecting to find actually. What is it? The acceleration, because delta v over delta t represents or indicates the acceleration of the object, the magnitude of the acceleration, which is the centripetal acceleration here. So then as an extension, I can say that delta v over delta t is acceleration ar is equal to v squared over r, right? This is an appropriate equation for the centripetal acceleration. Thank you for watching.